What's up, future engineers? I'm Yogesh, and welcome to CADMech, the channel that makes mechanical engineering simple and fun. Today, we're tackling the top engineering discipline questions every mechanical engineer must know. We'll cover fundamentals, machine design, heat transfer, and even the secret language of engineers, GD&T. This is your guide to acing interviews, exams, and truly understanding the core of our field. Grab your notebook and get ready for those aha moments as we connect theory to real-world machines. Are you ready? Let's begin. Let's start with the basics of mechanical engineering. Newton's second law, F equals mxa. Force causes acceleration. The bigger the mass, the more force you need. Stress is force per area. Strain is how much a material stretches. Pull a rubber band. Stress is the force. Strain is the stretch. Scalars have only magnitude. Vectors have magnitude and direction. Master these basics. They're the foundation of engineering. Thermodynamics and heat transfer. Energy can't be created or destroyed, only converted. Burn fuel in an engine? Chemical energy becomes heat, then mechanical work. Entropy always increases, energy spreads out, systems get more disordered. That's why perpetual motion is impossible. Heat moves by conduction, convection, and radiation. These laws power engines, fridges, and even your coffee cooling down. That's the magic of engineering. Can your design handle the load, or will it break? That's what strength of materials is all about. Imagine a diving board. Bending moment makes it flex, while shear force acts at the base. Young's modulus tells us how stiff a material is. Steel is stiff, rubber is stretchy. These concepts keep bridges, planes, and even chairs safe. This is the science of not breaking things. Now, let's make things move. Theory of machines and vibrations. The 4-bar linkage. 4 bars, 4 pivots. Change their lengths, and you get all kinds of motion, from windshield wipers to robots. Degree of freedom. DOF. How many independent movements a mechanism has? Most machines are designed for one DOF for control. Natural frequency. Every object vibrates at a certain frequency. Hit that frequency, resonance, and things can shake apart, like the Tacoma Narrows Bridge. Mastering these concepts lets you design smooth, reliable machines. It's the choreography of engineering. Create the motion you want, avoid the vibrations you don't. That's the art of machine design. Ready to design real parts? Let's dive in. Machine design is where theory becomes reality. Factor of safety. Always design parts to be stronger than needed. Uncertainties happen. Example. If a rope must hold 100 kilos, design it for 200 kilos. That's your insurance. Designing a shaft. Calculate forces, torque, bending. Pick a material, find the minimum diameter, and account for stress concentrations. Failure modes. Parts can break, fatigue, cracks from repeated loads, creep, slow deformation at high temp, or wear out. Good design anticipates and prevents failure. Use handbooks and data books. They're your best friends. Material selection is critical: steel, aluminum, polymers. Each has pros and cons. Informed choices make great designs. This is how ideas become real machines. Let's keep going. Next, making things cool. Time to get comfortable. Refrigeration and air conditioning. RAC. The vapor compression cycle. Compressor compresses gas. Condenser releases heat. Expansion valve drops pressure. Evaporator absorbs heat. COP, coefficient of performance, measures cooling efficiency. Higher. COP means better performance. Window AC versus split AC. Window AC has all parts in one box. Split AC separates noisy parts outside for quieter operation. Draw the cycle on a pH diagram to understand each step. Dive into psychrometrics to master humidity and comfort. Performance analysis is key. Always look for ways to improve efficiency. RAC is everywhere, from your fridge to your car. Master it, and you control comfort. Let's move on to fluids. Fluids are everywhere. Pipes, pumps, turbines, and wings. Bernoulli's equation. As fluid speed increases, pressure drops. This is how airplane wings lift. Cavitation. When pump pressure drops too low, vapor bubbles form and collapse, damaging the pump. Impulse versus reaction turbines. Impulse, Pelton wheel, uses fluid jets. Reaction, Francis Kaplan, uses pressure and velocity in submerged blades. These principles power water plants, dams, and city plumbing. Fluid mechanics is essential for infrastructure. Understand flow, pressure, and energy conversion. It's the backbone of modern engineering. Ready to make things? Let's talk manufacturing. Turning designs into reality. That's production and manufacturing. Casting versus forging. Casting pours molten metal into molds. Forging shapes solid metal with force. Stronger parts. Tolerances. No part is perfect. Tolerances define acceptable variation. Tight tolerances cost more. Welding. Joins metals using heat. Arc, gas, TIG, and MIG are common types. Know which process fits your part's shape, material, and strength needs. Specify tolerances that balance function and cost. Manufacturing knowledge makes you a practical engineer. It's how ideas become products. Next, the language of engineering. Engineers communicate with drawings, precise, universal, and clear. Orthographic projection, multiple 2D views, front, top, side, show every detail of a 3D part. GD&T, geometric dimensioning and tolerancing. The advanced grammar controls position and shape with symbols. Position tolerance controls where a feature like a hole can be. Profile tolerance controls the shape of complex surfaces. Feature control frame. The GD&T sentence. Symbol, tolerance, and reference datums. Reading and creating these drawings is a must-have skill. Accurate drawings prevent mistakes and make global manufacturing possible. This is the true language of engineering. Let's shift gears to cars. Let's zoom into automobile engineering, where all principles come together. Four-stroke engine intake draws in air fuel. Compression, power, ignition, exhaust, repeats thousands of times per minute. Differential lets wheels spin at different speeds during turns. Essential for smooth driving. Suspension, dependent, solid axle. Links wheels, independent, McPherson. Double wishbone lets each wheel move separately for better ride and handling. These basics are key for anyone passionate about cars or automotive design. Whether it's engines, safety, or performance, these principles drive the industry. The field is always evolving. Master the fundamentals, and you're ready for the fast lane. Let's wrap up. That's it. From physics laws to complex machines, these are the top questions every mechanical engineer should know. It's not just about memorizing, it's about understanding how the world works. Which topic should we deep dive next? Let us know in the comments. If this helped, like, subscribe, and share with your fellow engineers. Let's build a stronger engineering community together. This is CADMech, where engineering is made simple.